All good. Okay, excellent. Yeah, so thanks for having me, and it's good to see so many people actually in this InSAR workshop. It was exciting for the future of the field. Lots of people learning InSAR for I'm sure for a variety of applications. So you're going to get a different flavor of discussion, I think, in this lecture that I give from all of the others that you've received, in the sense that it's going to be less technical on the InSAR side and much more focused on interpretation of InSAR. So conceptual, the concepts that we use and thinking about how to infer various physical properties and so forth from InSAR. So that's pretty much where my research sits, and that of my research group sits, is in using large amounts of InSAR and other remote sensing data together to try to make inferences of various physical properties, particularly as related to glacier flow, ice sheet evolution, and so forth. So I'm going to try to tie all these things together, try to connect everything and ground it in some of the concepts that you've been learning so far, that Gareth has taught and teaching about the solid Earth, and then the technical aspects of InSAR. So we'll see where this goes. So anyhow, overview and objectives of this lecture. The main objective is going to be to provide a general introduction into the ways in which InSAR can be applied to the study of glaciers. So we're going to go over a brief introduction to glaciers. We're going to talk about some fundamental modes of glacier flow, their distinction from solid Earth deformation that Gareth talked about previously. And we're going to talk about how to relate InSAR observations to these fundamental modes of glacier flow so we can infer the properties that we want to infer from the observations that we can make. We're going to go over the relationships between observed surface velocity and velocity to other depths. We're going to go over different drivers of vertical displacement that exist in the natural systems. And then, well, we're not going to quite get to this, but in the Jupyter notebook, there's some discussions about various noise sources, common noise sources related to glaciers, and how these can create some interesting applications and challenges when using InSAR observations to study glacier flow. So glaciers, rivers of ice. They transport mass that's gained through snowfall at higher elevation to areas of mass loss at lower elevation. Okay, so we're accumulating mass at the top. Everything's flowing down under the weight of gravity. Mass loss occurs down here in what's called the ablation zone, either by melting off the surface, melting off of the base of the ice when it comes into contact with oceans and lakes, or calving of icebergs off the front. A little bit of mass is lost through sublimation, but that doesn't end up being terribly important in the overall scheme of mass loss. So glaciology, being the study of glaciers, can be broken down along many different lines. Some examples include the study of surface mass balance, that is rates of snowfall, wind speeds, melt, so on and so forth, and then glacier dynamics. Glacier dynamics is what I do. So InSAR is most commonly used to study glacier dynamics, but it can have other uses. In particular, some work has been done in the past by Howard Zebker and his group in particular at looking at estimating snow accumulation rates on glaciers using InSAR correlation. So I think Weber Cohen did some of that work, and if you're interested in it, feel free to look it up and dig into that. But basic takeaway from this is that I would argue that InSAR isn't used to its fullest potential in glaciology just yet. Most of the applications are focused on glacier dynamics, and that's the thing that we're going to talk about here today. So brief history on this, just because I think this kind of thing is fun. So since the 1990s, InSAR has proven to be an invaluable tool in understanding glaciers and ice sheets, how they respond to climate change and other environmental forcings. So I put this historic piece of literature here on the portal. I'm sure that Paul remembers this. I think he's old enough to remember that. This is from a paper from Goldstein and others published in 1993. It's published in Science, and I do believe this is one of the first interferograms that's published in literature. Certainly, I believe that one of the first interferograms of glacier flow in the literature. And this is kind of nice to me as well, because this area is near and dear to my heart, as we're going to go over in a little bit. But basically, you see an interferogram, like the kind of things that you've worked with so far. So you'll see the wrapping, the fringe rates. This is all done with ERS, so C-band radar. You'll see high fringe rates in some areas. We're going to talk about why that occurs in a little bit. Areas of what appear to be noise along these various strips, these things that are labeled marginal shear zones and so forth, and then a number of different densities of fringes around this image. We're going to kind of break down this image a little bit as we go along in this lecture, give you an idea of what all pieces of the puzzle you are seeing in all this. So in the early days, InSAR was limited to one or a few snapshots in a handful of areas like Rutherford Ice Stream that we just showed in this particular image. But after several years of research, data collection, lots of satellites and so forth, a more complete view of the spatial variability of ice flow in Greenland, Antarctica, and other glaciers around the world started to emerge. So this is the first, on the left-hand side, the first continent-wide map that we have of Antarctic flows cobbled together from pretty much all of the InSAR data that was available at the time. It's about 20 years worth of data at that time, all kind of stitched together to give us this general view of flow in Antarctica, where we have these relatively fast-flowing areas, as indicated on the color map here, that are concentrated in these streaming features, and then they tend to flow toward these larger areas of relatively fast flow. These are the floating ice shelves, the floating extensions of the ice sheet. And this is where pretty much all mass loss in Antarctica occurs. So in a nutshell, snowflake that falls anywhere in Antarctica is eventually compressed into glacier ice, flows through one of these fast flowing glaciers and ice streams, and is lost to the ocean and the ice shelf, either by melting off the base or calving off the front. So InSAR has proven invaluable in mapping these flow fields, as well as locating the point at which the ice starts to go afloat. That's an area that's called the grounding line. We're going to get back to that in a little bit. So delineating the difference between the floating ice and the grounded ice, and helping us dig in to understand these various patterns of flow. Why some areas are flowing faster than others. What are the consequences of that? What are the processes that give rise to that? Similarly, on the right-hand side, that's a figure I stole from one of Ian Jockin's papers. So Ian has done a lot of work, also stitching together lots of InSAR observations to give us this kind of complete view of flow in Greenland. Very different features in flow in Greenland versus Antarctica. To a good approximation, Greenland is kind of topographically controlled, so you have a lot of glaciers flowing through mountain ranges and so forth. At the edge, the fast flowing regions are kind of concentrated near the edge of the Greenland ice sheet. There's one ice stream up here in the northeast called the Northeast Greenland Ice Stream that extends relatively deep into the system. But and as a general rule, kind of flow properties in Greenland are a bit different than the flow properties in Antarctica. And there's a general lack of floating ice shelves and so forth in Antarctica. Or sorry, general lack of floating ice shelves in Greenland, lots of floating ice shelves in Antarctica. These are all things that were sorted out primarily with the use of InSAR. So you're all here to learn InSAR, though. Presumably most of you are starting out your career as scientists and practitioners of InSAR and so forth. So I wanted to make a brief note, kind of look into the future of InSAR for glaciers. So at this point in time, we have a pretty good understanding of the spatial variability in ice flow, largely through the work that I just showed you. So virtually all major kind of large scale, that is 100 meter or so, and persistent features of ice flow have been mapped up to this point. So there's not a lot left to do in terms of spatial coverage of InSAR observations within the cryosphere. Everything now kind of boils down to thinking about time variability, and then in some cases getting better spatial resolution in a few areas that are of interest. Now the time domain is, I think, the most interesting and exciting area of research. It's really not well understood, basically due to this historic lack of data. So I showed the map that Eric Rignot formed earlier in 2011. That was 20 years worth of data all piled together to make that single average velocity field. And we've gotten more and more data now, but we're still kind of to the point where we're usually happy if we can resolve the changes in glacier velocity at kind of monthly to annual timescales. But there are many shorter timescales that give us a lot of good keys into what's going on, ways in which we can probe the dynamics of the system to better understand the mechanics that allow for the flow that have not been explored in any meaningful way, simply because we haven't had the data or the people to do that kind of analysis. So if you're sitting in this class and you're learning InSAR and you're excited about glacier dynamics, I would strongly encourage you to start thinking about how you can extend efforts into the time domain and how you can infer time variation in glacier flow using stacks of InSAR observations or offset fields. And Brian Reel, my colleague, a longtime colleague, is going to give a lecture on that tomorrow, and kind of get you started looking at pieces of how to form offset fields and how to work with stacks of offset fields that are collected at different points in time. So all of the research, all of doing this kind of research, delving into the time domain and so forth, is just going to benefit from extensive data archives as new instruments and new time series tools are developed and put forward. A lot of the things that you're learning about in this course. So some recent examples of this work, I'm gonna take the liberty of emphasizing our own work within the field. This is some stuff that we published a few years ago now. It feels like ancient history, but it was, I think, one of the first time-dependent velocity fields that we got of an entire ice stream. So going back to Rutherford ice stream, which is the original image that I showed, and the Goldstein paper, that area of interest is actually located right around in here. So what we're looking at in this movie, though, as we play things forward, and what we're interested in is looking at the tidal variability of ice flow in this particular area. So we got a whole bunch of data collected from Cosmos SkyMed, which is a 4-satellite constellation that's operated by the Italian Space Agency. So Ozzy collected data for us for 8 continuous months, every single acquisition that they could get, over 39 unique flight tracks. So we had all these ascending and descending pairs that were stacked up that covered this entire area. So we did offset field tracking on all these things, ended up with something like 1,500 offset fields that we could work with that were collected over this 8-month period. We stacked all these things together, and then we inferred the sinusoidal variations in the horizontal flow, which is what we're showing here, as well as the vertical motion of the floating ice shelf due to the ocean tides that we'll get to in a little bit. So this is the result of that. What we're showing here is a total velocity field and how it changes in time. And on the right-hand side is variations in the velocity, all done with offset fields that Brian's going to talk about later. What we're showing along here on the bottom is a simple tidal model that just gives you a sense of kind of where we are in the tidal cycle. You'll see this general beat cycle, this low frequency cycle here. This is the spring neap tides. It all has to do with the alignment of the Earth, Moon, and the Sun. And it basically comes down to a period of half the period of the moon, so 14.77 days or so. That's the primary variability of the horizontal flow in Rutherford. So what we think is happening here is that the ice shelf is going up and down. It's changing what we call the buttressing stresses, or the resistive stresses that are provided by the ice shelf. As those resistive stresses change, the flow of the ice is enabled or is resisted, and the velocity of the glacier changes by about 20% or so over this 2-week, this fortnightly time period. And so on the right-hand side, we're seeing these variabilities. We see them change over the ice shelf, and then we watch these variabilities as we propagate into the grounded ice sheet itself. And that rate of propagation, the rate of attenuation of that propagation tells us a ton about the connection between the glacier and the solid Earth, how the ice deforms, and so on and so forth. Again, all done from SAR observations. Similar kind of thing that we published earlier this year. So this is a new deal. In the last one, we had to take advantage of the fact that we knew that the variability was sinusoidal in the velocities, and so we could stack up all of our observations and just infer the amplitude and the phase of a few components. In this case, we've extended those time series methods, and Brian's going to talk about a little bit tomorrow, to include more general variations in time. So in this case, what we're looking at is seasonal variations on Jakobshavn and Isbrae, also known as Cermak-Huzlek, which is located here in West Greenland. It's one of the fastest outlet glaciers in the world. So it's not shown in the video that the terminus position on this thing is changing, but it is changing over time, and that's causing the overall surface velocity of the glacier to respond. So we get to peak velocities during relatively warm years of 2012, 2013, 2014, and so forth. But what we're really interested in thinking about research is how this signal propagates through. So SAR ends up being the best tool that we have for this. Again, this is done with a big stack of offset fields, but what it does, it gives us the ability to resolve the spatial temporal variability in the glacier flow. So as the terminus position retreats, as surface melt makes it to the bed and lubricates the base of the glacier can accelerate. And we're really interested in how that acceleration moves through the system. That is the phase velocity and the decay length scale of the waves that are carrying the signal through the glacier, because these things give us unique insight, again, into the mechanics of ice flow, the kind of things that we really want to be able to infer from stuff. And final example of this, because I love movies, and hopefully you all like movies as well. This is some new stuff that we're doing, still working on in prep. We're looking at the response of, this is Pine Island Glacier, so a major outlet glacier in West Antarctica that is one of the major sources of sea level rise from the Antarctic continent. So here we're interested in how the flow of Pine Island Glacier changes in response to the ongoing disintegration of its floating ice shelf. So the ice shelf is shown in this area that's downstream of this black line. This black line is the grounding line, something that was found from looking at InSAR observations that we're going to talk about here in just a second. But what's interesting on the left-hand side and a bit you can see on the right-hand side are these SAR amplitude images in the background. So you can see these large chunks of ice as they're breaking off. You can see in these colored contours changes in the velocity field. You can watch the velocity field localize in these areas, because what's happening is that this margin over here that was resisting ice flow is disintegrating. As that margin disintegrates, these large icebergs break off. You can see the rifts forming in these in this ice. You can see those rifts as they propagate across to this other margin. And then you can see over here, what we're plotting is the relative velocity field, all taken from SAR offset fields. And you can see the glacier accelerate. You can watch this acceleration as it's coming up in this large calving event, moves across as that block goes. And then you see the acceleration as it starts in this margin, as the ice is disconnected from this area. And you can watch this signal as it propagates upstream, moves from the floating ice to the grounded ice. And understanding how that signal makes that transition from floating ice to grounded ice, and how it moves quickly, how it damps out, and so forth, is really key to our understanding of how the ice is coupled to the solid earth, what the proper rheology is, and really, at the end of the day, how to properly model all these things and represent it in projections of sea level rise. Okay, so with time-dependent observations, movies are fun, but when we get down to business, we think about the kind of things that we can track and observe. We can observe waves propagating through glaciers, something people have been after for a long time. We're finally able to do it. We're just starting to be able to do it because we have the data available to us. And you all, as you move forward and progress in your scientific career, you have more and more data available to you, more and more opportunities to do this kind of work, to track waves, to really think about the spatial and temporal variability, move beyond looking at snapshots, which is all people were able to do in the past. We can also look at localized deformation associated with ice fracturing. So you just saw in the last movie, the fractures that were forming, you can see these things in the SAR amplitude images, and we can pick them up in the offset fields as well. And if we take the offset fields, we form them into velocity fields. We take the gradient of that tells us about the strain rate, the deformation rate of the material, which is directly relatable to the stresses. And that's the thing that we care about, because we want to understand under what stress conditions ice fractures, under what stress conditions do these rifts break off, start to drive the flow of ice, because this is one of the essential features for better understanding how glaciers and ice sheets are going to evolve as the climate changes. We can look at it, we can understand ephemeral grounding of the floating ice shells. So that map of the grounding line we talked about before, that's picked out from InSAR observations, as we'll talk about in a bit. It's basically looking at the change in the vertical displacement that's picked up by InSAR over the floating ice shelves. And finally, we can look at spatial variability, spatially varying amplitudes of the ocean tides under floating ice. The first example that I showed you, we were able to do that kind of thing. We actually made one of the first sort of maps of what the ocean tidal amplitude and phase looks like under these areas. And we did it all with time series of SAR observations. And there's so much more we can do, so much more stuff that I've never thought of, that anybody else has ever thought of. And so if you come at this, learn the technical skills in this class, throw a creative mind to it, you'll do amazing things. So time dependence, again, I can't stress this enough, is really the new frontier of research in InSAR and other remote sensing observations, particularly as it pertains to glaciology. And there's loads of work to do, loads of opportunities to make fundamental contributions. So since Gareth talked somewhat in a previous class about thinking about solid Earth and modeling InSAR observations that are collected over the solid Earth, I wanted to try to give you a brief connection between glaciers and the solid Earth. So when you're thinking about glacier flow, connected to something that you've learned already. So we'll start off with some basics. So I'm assuming that not everybody is an expert in continuum mechanics when it comes to this class. If you are, apologies for boring you on this. But from a mechanics perspective, solid Earth is a solid. Solids are defined as things that can support shear stresses for relatively long periods of time. Glacier ice is a fluid, and fluids are defined as materials that deform continuously under applied shear stresses. And just make a brief note here that we use fluid and solid here to describe the mechanical properties of materials and not the states of matter. So liquids is a description of the state of matter. Liquids are fluids, but fluids are not necessarily liquids. Fluids can be things that are in any state of matter: solid, liquid, gas, plasma. So ice is a polycrystalline solid, here using solid to describe the state of matter, and it flows as a viscous fluid over timescales that are observable with InSAR, which is to say that over timescales longer than about a day, maybe a week, in some cases where the ice is really cold, the ice is a viscous fluid, and it flows just as a viscous fluid, just like syrup or honey spreading across the plate. Now, the deformation and the flow of ice is facilitated by the motion of voids and dislocations. You might think of these as imperfections at the molecular scale in the material. And these voids and dislocations are able to move within and between individual ice crystals. Two primary modes of deformation that we'll talk about here today. There are others, but these are just the basic ones. Diffusion creep, which is the motion of void spaces within the crystalline lattice. These void spaces move or they diffuse through the crystalline lattice in response to applied stress. So the material relaxes as these void spaces move through. All materials have void spaces. You cannot have a material, particularly one in steady state, that has no void spaces. It's not energetically favorable to do that. It's most energetically favorable to have at least some void spaces in the material, and then those allow the material to deform fairly readily. In addition to that, ice, polycrystalline material, lots of water molecules, just H's and O's, they're all connected together. Individual water molecules are connected into the crystalline structure of the ice through hydrogen bonding and so forth. Those connections are imperfect. You put all of these things together and there will be what we call dislocations, places where there maybe should be a bond, but that bond is not able to be connected. So as the material is sheared, that dislocation, that connection moves through the material and the actual structure kind of moves in a stepwise fashion. The analogy of this is if you wanted to try to pull a rug across the floor, it would be really hard to pull the entire rug. Instead, you can make a wrinkle in the rug, and then you can move that wrinkle all the way down, and you can move the rug in fairly short order. Materials like ice move in the same kind of way. Imperfections, those imperfections allow for localization of stresses that mobilize individual pieces and connections at the molecular scale, allow the material to deform. Whew, should probably pick it up. Just a brief side note, this is the kind of stuff that I love. So obviously we're spending a lot more time on it than maybe we should have. But maybe the fun part about all this and thinking about the InSAR observations is that this dependence of ice flow and creep mechanisms means that we can use InSAR observations that are collected from satellites to infer the motion of water molecules that are going on in the ice. And I think that that's awesome. That's like 15 orders of magnitude in terms of spatial scale separation, which I think is absolutely epic. And one of the funnest things about doing this kind of remote sensing work and looking at how glaciers in particular flow and deform in the earth. But to make these kind of inferences, to really sort of get at what's going on, we have to understand the connections between what we observe and what we want to know. Now, we can describe the flow, deformation, and fracture of materials in a variety of ways, but basically two main ways that we describe them. We can describe them in terms of motion. This is referred to as a kinematic description, and we can describe them in terms of forces that drive that motion. That's a dynamical description. InSAR gives us kinematic quantities, and we often want to relate these kinematic quantities to the dynamics, so the forces that are driving the motion and the processes that allow it. So solids versus fluids, usually we're interested in different but related kinematic InSAR observations because the dynamical descriptions differ. In solids, what we often care about is looking at the displacement and the deformation. Deformation being the gradient of displacement, which is related to strain, which is most simply defined in its uniaxial sense as the change in length over the total length of something like a bar. So if I took my pen, I stretch it out, the change in length of that pen over the original length is strain. Now, an idealized, at least linear elastic material, stress is proportional to the strain. So what we're interested in observing are these deformation fields, the gradients of displacement and so forth, and in order to get at a better understanding of the overall stress field. In fluids, at least an ideal fluid, strain doesn't matter at all. We don't care about strain. What we care about is the rate of deformation, what is sometimes called the strain rate. So we're most interested in using InSAR observations to get at velocities and the gradients of velocities, because it's the gradients of velocities are also called strain rate that are directly relatable to stress. And in material like ice, there's a nonlinear relationship between the stress and the strain rate that we can observe. These are often related in power law form, where we get an exponent n that ranges typically somewhere between 2 and 5. And this value of n, and the changes in the value of n, really have important implications for InSAR observations of glacier flow. So to dig into this a little bit more, strain rate scales as stress raised to the n value. So n is the exponent on the stresses itself. And because of this, we can relate then the viscosity of the ice to the stress, which is viscosity scales as stress raised to the 1 minus n power. And so any changes in the value of n then has a major influence on the local viscosity of the ice, which in turn then has a major influence on the deformation and the InSAR observations that you make. So just kind of hammer this down in the things that you know. N equals 1 is a Newtonian fluid. That simply means that the viscosity is independent of stress. So liquid water is a Newtonian fluid. But glacier ice, like we mentioned before, it has values of n somewhere between 2 and 5. Although I'll just point out that calibrating the value of n is very much an active area of research that InSAR can contribute directly to. So with values of n greater than 1, we can plug this in and we can say we get a negative exponent value on stress. And what that means is that viscosity decreases as stress increases. So as we increase stress, viscosity decreases. That softens the ice, that localizes the deformation, and that makes InSAR observations in many ways more interesting. We get higher fringe rates in these areas. We have sometimes a harder time unwrapping these things. So the dependence on viscosity and stress is really a thing that we get excited about. I certainly get very excited about. But the obvious question is, what sort of determines this value of n? And the short answer is the creep mechanisms that we discussed previously. So diffusion creep, we'll get n equals 1, so we get a Newtonian fluid, which is kind of boring. But pretty much everywhere in ice, or at least everywhere in ice on Earth under terrestrial conditions, we'll typically see a significant contribution of dislocation creep that we talked about before, this motion of carpet across the floor. Dislocation creep requires n values typically of 3 or more, probably in the 4 range, but we're still working on this kind of thing. Now that all assumes that the ice lattice is still relatively intact, but if we get a lot of damage going on, the disintegration that we saw in pig before and so forth, we get plastic deformation in the ice or failure of the ice, and this sort of thing can result in a very large value of n. In fact, n will go to infinity for a perfect failure, a rifting of the ice itself, and a sliding of 2 blocks relative to one another. And so this kind of thing basically ends up looking like an earthquake, so faulting that you see in the InSAR observations you saw before. The creep mechanisms have less interesting values of n, they're closer to 1. So this value of n really creates these interesting challenges and opportunities for InSAR observations, and we're going to dive into how that works now. So thinking about the fundamental modes of glacier flow, and how we relate these kind of things to observations. We can step back and kind of justify the things that we're doing by thinking about 2 basic facts that drive a lot of work in geophysics and other scientific fields, and something worth keeping in mind when thinking about InSAR observations. First is that we can only observe a small subset of the things that we want to know. And the second is that observations are facts. And science progresses through the development of organizing principles that make sense of these facts, right? And so then the basic questions are then, how do we relate the things that we can observe to the things that we want to know, and how do we organize and interpret the observations that we want to make? That's sort of the gist of what we're talking about today. So in general, it's through inference using observations to test and constrain models. With InSAR, we can measure glacier flow velocity at the very near surface. So there's going to be some non-zero penetration depth of the radar, but for the most part, we are measuring the velocity of the surface of the glacier itself. But often we want to know how the ice velocity varies with depth. So how fast is the glacier actually slipping along its bed? And that's not something that we're currently able to measure directly, certainly not using InSAR. So when we think about this kind of thing, and we think about the relationship between what we can observe and what we often want to know, we can think about two end-member models for glacier flow and how the glacier flow varies as a function of depth. There's a vertical shear dominated flow, and this is basically ice that's frozen to the bed. And as it's flowing along, everything's just deforming, and you get this gradient of deformation near the bed that tends to taper off. And the slope of this deformation and this overall shape and the tendency for it to taper off is all a function of this exponent n that we were talking about before. In fact, then the surface velocity simply scales as the ice thickness raised to this n+1 power. And then in the most extreme case, the end-member case, this velocity at the bed itself is equal to 0. The opposite end-member case is when the surface velocity is equal to the velocity at the bed. And then this kind of thing depends less on the overall thickness of the ice, and it depends more on the width of the glacier, the kind of thing that we can actually observe. So it ends up scaling as width to the n+1. And again, this kind of shape is driven by this value of n, the kind of thing that we can really start to pick apart when using InSAR observations. Now, which one of these flow regimes best represents your area of interest is likely to have a major influence on your inference of your InSAR results. So if you're sitting in this class and you're thinking about using InSAR for glacier observations, just keep in mind this type of variability. It's common to simply assume one or the other within the field, but it's good to keep in mind that those are assumptions very often and not necessarily things that we have a great sense of or a great understanding of. So we're going to focus here after, though, just to get down a few more concepts before we get to the end of all this. On basal slip dominated flows, it's the easiest regime to visualize using InSAR. Again, the velocity simply goes as the width raised to the n+1 power, and this overall shape is dominated by the value of n. So as n becomes very large, you're just localizing more deformation and so forth toward the margin. So this value of n, or the rheology of the ice overall, is going to vary according to the creep mechanisms, the temperature of the ice, and a whole host of other factors that I'm happy to drone on about at length for those of you who are interested. But all these things can vary in space, and they're generally sensitive to the rate of deformation itself. And the sensitivity of rheology to deformation and deformation to rheology creates this whole host of absolutely amazing feedbacks within the system that we really don't understand well at all, and could definitely be studied with InSAR observations, which is a hint for anyone who's looking for incredibly challenging physics problems. But these feedback mechanisms basically soften ice in areas of high deformation, which drives further concentration of deformation. Why does all this matter? For InSAR observations, it's basically that softer ice ends up giving you higher rates of deformation, which ends up being challenging for doing things like unwrapping and processing of your InSAR data. So this is just an example, cross-flow profile of the velocity of an idealized ice stream. So we have the observations that are focused here in the yellow lines. This is taken from the Rutherford data that we showed earlier, and then a few idealized models to show you the change in the n value from 5 to 3. So in the actual system, what we end up with are steeper gradients in the overall velocity field that is significantly higher strain rates than what we might expect from an idealized model using any of the canonical values of the overall exponent. In this area, what we infer is what's happening is that the crystalline properties of the ice are changing. So ice crystals are starting to align with one another, temperatures are going up, ice is softening, and so forth. But in this area, we kind of bumped into this when we were first processing the InSAR data, basically because we were not able to unwrap across the shear margins in this area because of the fringe rate overall was just entirely too high to deal with. So hammering on that point a little bit more and going back to the Goldstein data that we showed before and thinking about how this impacts the interferograms, particularly the wrapped interferogram that you see in this area, this localization of deformation really manifests in these incredibly high strain rates. So the plot that I just showed you is a transect that goes right across the ice stream in this particular area. And so these bands that are going down here are the shear margins of the ice stream. They're lit up in the back because this interferogram is plotted over top of the amplitude images. The high strain rates create a lot of damage, and the crevasses and the damaged ice and so forth like to reflect a lot of radar power back to the instrument. But you can notice that all this basically looks like noise. There's almost nothing in the way of coherent fringes across these margins because the deformation is so localized, because the deformation rate is so high. And in this case, I'm sure that they weren't able to unwrap across these shear margins. When we did this kind of work with Cosmos SkyMed and one day repeat with X-band, we occasionally were able to unwrap across these margins, but for the most part, we had a really tough time. So if you're wanting to use InSAR in these kind of areas, you have to be very careful in your unwrapping, and you have to be mindful of, I guess, the conversation that was taking place whenever I popped in to this Zoom meeting. Okay, so we're going to shift gears a little bit and consider complicating factors that can arise in using InSAR to measure glacier flow, and namely different sources of observed vertical displacement. And this is the thing that we're going to wrap up on. So you'll recall, and I'm sure you've figured out by now, InSAR measures the displacement along the radar line of sight, right? And so there are multiple factors that can be broadly defined as vertical displacement or vertical velocity that can then manifest in InSAR observations in line of sight displacement. So it's important to understand the differences between these things that we may consider to be vertical displacement so that you can sort out what the main contribution is in these areas, correct your data as you need to in order to do the studies that you want to do. Four main factors of the vertical velocity associated with the flow of the ice itself: vertical displacement due to the bulk motion of the glacier that is rising and falling. Typically, this happens over the floating ice shelves due to ocean tides, changes in the surface elevation of the glacier, and changes in radar penetration depth. We'll go over these first couple, and then we'll call it a day. There's some lengthier discussion of radar penetration depth and other things in the Jupiter notebook. So the vertical velocity due to flow. So glacier is simply accumulating snow at high elevations. It's flowing, it's melting at lower elevations as it flows downhill. In order to conserve mass, a glacier that is at or near steady state has to have a vertical velocity associated with it that maintains its thickness over time. So as snow falls, a particular parcel of ice needs to respond to that and have a downward velocity within the accumulation zone that is a flow into the glacier, as they're attempting to represent in these purple arrows here, such that that parcel of ice moves through. That is, that there's some time dependence to the depth of any given parcel of ice. Similarly, in the ablation zone, where mass is lost, the same parcel is going to move toward the surface as the ice flows. So in InSAR, this process can manifest itself as the vertical motion of the scatter itself. The vertical velocity in general is very small relative to the horizontal velocities, and is often ignored in standard glacier velocity products, but it can be of significant interest, particularly for those of us who want to do detailed observations of what's happening at the bed, the coupling of the ice in the solid earth, and so forth. But it's really important to be careful of what you're inferring whenever you're inferring glacier velocity, and whether or not you're actually inferring the vertical component of the velocity itself, or you're simply inferring changes in the surface elevation of the glacier. These two things should not be confused, as they are different mechanisms, but they can manifest themselves in very similar ways within the observations. I'm happy to talk with you at length offline about ways in which we can distinguish those two things. Well, we'll wrap everything up, going back to this fun image and thinking about this wrapped interferogram from Goldstein and others, and looking at these areas upstream that have these relatively high fringe rates. You can see this kind of horn-like feature and so forth in these higher fringe rate areas, and then you see these lower fringe rates in the surrounding areas. Now, this is labeled the grounding line here. We talked about the grounding line before. It's the thing that separates the grounded ice upstream from the floating ice downstream. So these fringes that you're observing is the vertical motion of the floating ice shelf itself in response to the ocean tides. And we can take these kind of things and we can cast them in a time series sense, as we see here. These are the Cosmos SkyMed observations that we used to make the movie of tidal variability before. And you can see how this vertical motion of the tides really starts to manifest in the line of sight observations within the glacier. So all these things were taken in the same 8-month period. So there's not a whole lot of time between the oldest and the newest of the observations within this link. And you can see that the observed line of sight displacement changes quite significantly between these observations. We see this horn-like pattern that's represented in the grounding line that Goldstein and others had plotted out before. And this is typically the common way in which we use InSAR to map the position of this grounding line. The grounding line is kind of the a good way to take stock of the state of the ice sheet, the position of the grounding line and how it changes in time. So a lot of work goes into thinking about how to precisely map the position of the grounding line using this tidal flexure that's picked up in the InSAR observations. So all this kind of thing just begins to barely scratch the surface on using InSAR observations to observe glaciers. So there's a lot more in the Jupyter notebook that goes with this lecture. So in that notebook, you can read about changes in electromagnetic properties, how they influence InSAR observations. You can read about common sources of noise and error and InSAR observations of glaciers and so forth. But to just kind of wrap things up and to get us going, finishing up on time, glaciers, I would argue, are among the most exciting and challenging features of Earth that can be studied with InSAR. In essence, glaciers are geological processes that are playing out over human timescale. And so what you're learning in InSAR within this UNAVCO course can simply be applied to glaciers, so long as you keep in mind a number of kind of unique factors of observing glaciers, some interesting challenges and opportunities and so forth with using InSAR and SAR observations in general when studying glaciers. But in essence, what we've gotten to is this point where we can start to map out these huge flow features across the entire continent of Antarctica. So this is basically a redo of the Regnault et al. Map that I showed earlier. It piles a lot more data in, but really emphasizes, I think, the nature of the streaming flow that we observe in Antarctica. And we have a map of the continental US on the back to give you the sense of scale. This amazing tool that we have, InSAR observations and remote sensing in general, to be able to visualize all these things that are going on. And now in the future, we're basically going to take maps like this and we're going to stack them up in the time domain. And we're going to be able to do a lot more studies and thinking about how these features evolve and respond to things like tides, calving of icebergs, and so forth. And all of that will give us these incredible windows into how these systems work, how we might expect them to evolve in the future, and so forth. So what we've covered in this lecture, this is a very brief whistle-stop tour, but we worked through the relationship between observed surface velocity and the properties that we may observe at depth at a very, very high level. We talked about a little bit about the InSAR, the influence of ice rheology and InSAR observations, in particular the challenges of unwrapping across rapidly deformed areas like shear margins. We often get around this challenge of unwrapping and so forth, or the various challenges related to InSAR, because we often end up just doing offset fields, pixel tracking, speckle tracking, whatever you want to call it. And that is the thing that Brian is going to talk about in his lecture tomorrow. He's going to walk you through some technical details about how those offset fields are made, how we put them together into a stack, how we think about the time variation that we observe within these offset fields. Multiple mechanisms that can manifest as vertical motion in InSAR observations, from flow of the ocean to, some flow of the glacier to ocean tidal uplift and changes in glacier surface elevation and so forth are all things to keep in mind whenever you're making InSAR observations. So there's so much more to do with this. As Paul mentioned, I'm a bit on the busy side these days, so I threw together what I thought would be a few interesting conceptual topics for you all. But it's a huge field, a huge area, and it's growing very fast. There are tons of opportunities for InSAR specialists to contribute to glacier dynamics. So I hope some of you will at least take some interest. It's an endlessly fascinating topic, a lot of great stuff to do, a lot of fun physics to work out. So check out the Jupyter Notebook for more. If you're super excited about this kind of thing, reach out to me. I'm happy to talk to you. So that's all I got.
Great. Thank you so much, Brent. Really interesting stuff. I have about 1 billion questions on it, but I'm going to let the students ask questions.
There is a question in the chat. I'm not sure, Brent, if you see it.
Oh yeah, what platform do we use to process SAR data? So in the past, we've used ICE. Some of the stuff that we use, at least in like the movies that you observe, are things that are processed by other people. So there are a lot of large soft money groups out there that are processing the offset fields and then making those things available to the broader community. So a lot of that stuff is processed by Ian Jochen, who I think has a lot of some cobbled together combination of various tools that he's collected over time. But whenever we process our data, we do it all with ISCE. Hopefully that's what you mean by platform. Marianne, is that your name? You have a hand up?
Yeah, hi, thanks for your talk. I was wondering if you could talk a little bit about applications to glaciers that are in other situations. So you talked about Greenland and Antarctica, but have people worked on glaciers that are like in mountains or more complex topography? And are there additional things you have to worry about when looking at things that might be at weird angles?
For sure. Yeah, people have looked at these things kind of all over the place. So yeah, whenever you're dealing with in mountains, of course, you have to deal with the basic shadowing and layover and so forth that occurs whenever you're looking at SAR in any kind of area with high topography. But other than that, in terms of InSAR, I don't know of any significant geometric challenges outside of those things. Just as long as you have a reasonable DEM of the surface, you can calculate what the local incidence angle is and try to work out the relationship then between the glacier velocity vector and the line of sight vector that you're making observations along. In mountains, of course, you run into all kinds of things like surface melt, for example. There's a whole bit in the Jupyter notebook talking about the challenges associated with surface melt and using InSAR observations in areas and during times in which the glacier is melting. These are not issues that we run into in Antarctica. They are issues in Greenland and certainly in a lot of mountain glaciers throughout the world. So does that answer your question?
Yeah, thank you.
Mm-hmm. Parvis, is that right?
Yeah, thanks for a great talk. That was so interesting. To be honest, I didn't think that actually InSAR can have a really good results in ice and snow because of the noise. But these results are so amazing. I have a lot of questions, but maybe just ask one or two.
Yeah.
The first thing, I guess, because I'm mainly working on Greenland and about projecting the RSL here or the glacier or other things. One of the key elements here to be able to project the glacial change or the change in other part is that to eliminate or remove the GIA signal, because the recent observation contains this signal and we need to remove this to be able to interpret the actual signal. And I know that there has been some studies about this region and this kind of thing to be able to reconcile the difference between the GPS observation and what we see now today. So there has been a lot of problem in that case because they just assume a linear hydrological between the solid Earths. And I just wanted to know that, do you work on removing the GA signal here, or did you have any problem in that case?
No, so we don't work on directly removing it, basically because, well, one, we haven't run into this particular issue. Two, what we end up doing is tying the interferograms that we make or the offset fields that we make to some ground control points, and so those things are moving with they have more or less the same GIA signal as anything else, and so we tie those features, subtract out kind of a surface fit to the slow moving areas and so forth, and end up with the residual that's left over, which is the fast flowing bits. That said, if you were looking at, we pretty much always focus on very fast flowing areas. So like Pine Island Glacier is flowing at 4 kilometers per year and is very focused channel. Jakobshavn is flowing at something like 12 kilometers per year or something like that in a relatively narrow channel. And so those signals are so huge relative to something that you would expect from GIA, which is going to be at most, kind of millimeters to centimeters per year, that we we tend to not run into that in our studies as being a major source of error. But if you're looking at slower moving areas, it sounds like you running into that challenge. I would assume that hopefully there's some halfway decent models on mantle viscosity and uplift and so forth from GPS observations that you could at least get kind of a first order rough fit to GIA, but I don't know.
Yeah, I see. Maybe in a very small area that wouldn't be an issue, because I saw that the Greenland InSAR and just wondered that where is the reference point here, because the GIA signal is too different in the whole of the region. So for InSAR, we need a reference in space and in time. But for space, we don't know actually the GIA signal in that area, and we have problem to actually simulate that signal. Okay, it's one of that, and the other one is that do you account for other things like basal temperature or surface heat flow to model your ice flow, or just you are considering the things above the solid earth?
Yeah, so it depends on what kind of modeling we're doing, basically. So a lot of the modeling that we do, at least related to the InSAR stuff, is the inverse problem. And in the inverse problem, basically what we're looking at often is things like inferring the drag at the base of the ice and so forth, which will be a function of geothermal heat flow, temperature of the bed, and all this kind of thing. But it's not those are not processes that we need to account for within the model, because they're all embedded in the inferred parameter that we end up getting out. We tend to not go much beyond that in terms of trying to extract things like estimates of heat flow or frictional heating, geothermal heating, whatever it is at the bed, from these inferred values, simply because we don't trust the inferred values all that much. And then there are also all kinds of complicating factors, like these values of drag are going to be functions of localized water pressure. They're going to be functions of roughness of the bed. They're going to be functions of a lot of things, including heat flow and temperature and things of this nature. And we just don't have any way to control for the other factors at this particular point in time. We're usually just happy to get any kind of inferences of drag that we can get, and then ideally trying to relate those inferences of drag to the observed surface velocity so that we can work out what the right basal boundary condition is within models. At least when I say basal boundary condition, what I mean is what's typically called the sliding wall, the relationship between drag and velocity.
Yeah, you're right. In Greenland and also South Pole, the surface heat flow is one of the issues, because we don't have any actual results, and all of the models are different from each other. And at the last, you mentioned that there are lots of fringes in many glacier part. Have you tested a larger wavelength like L bands or S band, because of the wavelengths you can see lower fringe that makes it even easier to unwrap the face?
Yeah, for sure. I mean, we take what we get in terms of data. It's often not up to us what frequencies are used, and so yeah, we're certainly happy with lower frequencies. And like when ISAR flies, it'll have a number of great. And we're just going to collect all kinds of data, and we'll probably not run into the same fringe rates. But up until now, in a lot of cases, what we had available to us is X-band. And so we kind of had to live with high frequencies, even though that's not necessarily what we want.
Maybe it's because of the penetration, because if you use a lower frequency, your signal would penetrate much more, and maybe it complicated the result as well.
Yeah, I mean, we're fine with that kind of penetration. It's just mostly that we're not always the most important. We're not always the sole consideration when people are designing instruments. Do we want to, Franz, I see that you unmuted. Do we want to do a few more questions in the chat, or do we want to call it?
Yeah, let's maybe, there's a couple of questions that are related that talk about how do you get from line of sight velocity to either a surface parallel flow velocity, or how are the velocities projected? There's two questions related to that by Quinn and by Riley, I think.
Yeah. So you can so there are two different options for this kind of thing. In an ideal world, you would have enough diversity in line of sight views to be able to simply invert for the velocity vector as you have it. So that's going to require at least 3 unique line of sight vectors and taking either InSAR observations or the offset fields along those lines of sight. You can do it with ascending and descending orbits on satellites, so long as you have some estimate of the offsets in the azimuth direction, either by multi-aperture interferometry or the offset fields. So Brian's going to go over that in a little bit. If you only have 2 line of sight or even a single line of sight, then you have to have a good digital elevation model. And so you can take that DEM and you can calculate, basically you can take the assumption that the velocity vector is along the gradient of the surface. And then you can say that the line of sight observation that you make, the displacement along the radar line of sight, is simply the dot product of the velocity vector, which is given to you by the DEM, and the line of sight observation that you get. And so from there, it's just a straightforward geometric problem to work out how to calculate the surface parallel component of flow. So hopefully that answers your question.